Okay, so we have an exam a week from tomorrow. It's pretty scary. It's coming out. I still have to write your exam, so. So anyway, I'll be sure to make your problems extra hard because you're such a great class.
If you need help with writing it, you can send me a copy.
Sure. Okay, but so during problem solving today, I do need to discuss some things with the lab tomorrow. But after that, I want to just dedicate a couple hours to continuing to do some problem solving for the material for the exam coming up. And then next Friday we'll also do more problem solving for the exam coming up. So hopefully that, along with all the studying you're doing outside of class, right? Wink, wink. You'll be prepared for the exam. All right. So on the agenda for today, we will finish chapter 4, and we'll start chapter 5 on gases. The only thing we have to finish in chapter 4 is redox reactions, specifically balancing redox reactions. So, how many of you remember doing balancing redox reactions from Chem 107? You should have had balancing in acidic and basic conditions. So I'll go through the process of balancing, and I'll do an example where you do both acidic and basic conditions. So. Okay, so balanced redox reactions. With redox reactions, you have to worry about balancing the electrons in addition to balancing the atoms. We do this using a method called the half reaction method. Okay. So the first and foremost thing you have to do with a redox reaction, you're going to be given a reaction, and you're going to have to figure out which reaction or which half reaction is reduction, which is oxidation. And to do that, you have to first look at the oxidation numbers of all the elements. Okay, so first of all, we were practicing oxidation numbers, right? So you look at all the oxidation numbers of the atoms, then you split the whole reaction into two half reactions based on the oxidation numbers. So if you look at the oxidation numbers, you can look at those and know what's being reduced and what's being oxidized. And so based on that, you'll break up the reaction into two half reactions. And once you have two half reactions going, then you do a process that I call Mohi. Okay, anyone ever heard of Mohi before? No? If you were in my class, or 107, you may have heard of Mohi. Mohi is an acronym for the process in which you should balance these half reactions. So for each half reaction, you balance the miscellaneous atoms first. Miscellaneous being all atoms except for oxygen and hydrogen and the electrons themselves. So at that point, once you balance those atoms, you balance the oxygen atoms using water. Okay, so you would add water to the oxygen deficient side. And then once you do that, you balance the hydrogen atoms by adding H+ to the hydrogen deficient side. And then you balance the electrons last by adding electrons on the appropriate side to make sure the charges are the same on both sides of the arrow. Okay, so it'll be easier if you just watch me do an example if you haven't seen it before. At some point, you might need to equalize the electrons transferred on both sides of the reaction. In other words, electrons flowing from the oxidation half needs to go to the reduction half, the same electrons. And then at the end, you recombine the half reactions and you get an overall balanced redox reaction. If under basic conditions, you just take whatever you have from the process and add OH to both sides where there's H+. Okay. Or add OH to both sides, but equal to the number of H+ ions in the reaction. Okay, so let's just look at this example. So it says here, balance the following under basic conditions. In order to get to basic conditions, you have to balance in acidic conditions. So really, this is doing both. You've got chromium 3 oxide reacting with hypochlorite ion. Notice how I'm reeling off the nomenclature still, right? And it reacts to produce, what's this called? Chromate and chloride ion. Okay, so that's the overall redox reaction, but it's unbalanced. Okay, so in order to balance this, what was that?
CR203 was?
Cr2O3 is chromium 3 oxide, right? So this subscript 3 becomes the 3 plus charge on the chromium. Okay, and the 2 minus goes to the oxide. So chromium 3 oxide. Okay, ionic compound, covalent compound, monatomic ion, not ionic or covalent, just an atom by itself. So just a little review of nomenclature. Okay, so so the first thing we do is we got to look at the oxidation numbers. So what are the oxidation numbers in chromium 3 oxide? So oxygen's always -2, virtually always -2, and as a result the chromium has to be, well, we said it in the name, chromium 3 oxide, so it tells you that oxidation state of the chromium is +3. Okay, and then you have hypochlorite. Again, oxygen is always -2, so what does the chlorine have to be? +1. And then you have chromate. Oxygen is always -2. So what does the chromium have to be? I hear whispers of +6, and you would be right. Is everybody okay with how I got that? All right, so 4 oxygens times a -2 gives me -8 from the oxygen. +6 is still -2 overall, right? Which is what we want. And then the chloride ion is -1, right? So we look at those oxidation numbers, and at that point we can decipher which one is reduction, which one's oxidation. So what's happening to the chromium? It's becoming oxidized, and so we can write the oxidation half as Cr2O3 goes to CrO4 2 negative. All right, that would be our oxidation half. And then by default, the rest of it is the reduction half. So we have ClO negative and Cl minus. And of course, the chlorine with +1 and -1, that's gaining electrons, so that's reduction, right? Okay. Are you with me so far? Okay. So we looked at the oxidation numbers. We used those oxidation numbers to split the reactions in half. What might be a faster way of splitting these up rather than looking at the oxidation numbers? There's a slightly easier way to do it. What's another way of telling if something's getting oxidized? If it gains oxygen, right? So you look at chromium, okay, it's a 2 to 3 ratio, now it's a 1 to 4 ratio. So it's got more oxygen per chromium atom. That's oxidation too. Right, you look at hypochlorite, it lost oxygen, that's reduction. Right, can you see how that, it could make life easier? But if you're unsure, you could do the oxidation numbers. So now that we have our half reactions, now we do the process of Mohi. So what does the M stand for again? Balance miscellaneous atoms first. So miscellaneous atoms in this case constitute chromium and the chlorine. Balancing the chromium, how do we do that? Yeah, we put a 2 in front there. And in balancing the chlorine, are we balanced for the reduction half? And yeah, we're balanced. Okay, so that's the M done. Now what do? We do the O part. So O is balancing oxygen by adding water to the oxygen deficient side. So for the oxidation half, do I have an oxygen deficient side here? Yes. So I've got 8 oxygens here. I only have 3 oxygens here. So how many waters do I add and to which side?
5.
I add 5 waters to which side? The left side or the right side of the arrow? Left side. All right, so I'm going to add 5 waters to the left side. Okay. What about the reduction half? How many waters do I add to which side? Yeah, 1 water, but to the right side. All right, we're done with the O part. Yeah, question.
Can you get the 5 waters again?
So I have 2 times 4 is 8. O is on that side. I've got 3 O's here, so I have to add 5 waters to get 5 oxygens from that. Got it. Now for the H part, so it's Mo-He. Okay. So now we add H plus to the hydrogen deficient sides. So how many H pluses do I add, and to which side for the oxygen half reaction, or oxidized half reaction? Yeah, I've got 10 hydrogen plus ions now, right? So 10H plus. Okay, and what about the bottom reaction? Okay, I gotta add 2H plus to that side. Okay, everybody all right with that? It's a process you have to go through. If you don't follow it in order, you could mess it up by accident. So now we've got our H plus added. Okay, what's the last part? We've done Mo with the H. What's the last letter? E, electrons, right? So at this point, we're not going to look at the atoms themselves, but we're just going to look at the charge. So if I look at my oxidation half reaction, I've got 2 times a -2 charge. That's a -4 charge from that, plus 10 plus 1s from this, from the H plus. So overall, what's my charge on the right side of the arrow for the oxidation half reaction? I've got a +6 overall charge. What's my charge on the left side of the arrow for the oxidation half reaction? 0. So where could I add electrons and how many to make sure that the charges on both sides of the arrow are 0? Yeah, I can add 6 electrons to the right-hand side to make sure that now the right-hand side would be neutral. Okay. If I added 6 electrons to this side, I would have a -6 charge overall then to the left side, and it still wouldn't get me the same charge as this side. It would have +6. So +6 and -6, that doesn't match, right? So you want the charges to match on both sides of the arrow. So to do that, let's go ahead and add 6 electrons to the right side. And then for the reduction half reaction, where could I add electrons and how many to make it the same on both sides, same charge on both sides? So I've got -1 overall on the right-hand side of the arrow. I've got +1 overall on the left side of the arrow. Does everybody see that? So to make this, how can I make this -1 or +1 on both sides? Yeah, so to the left side, I have to add how many? 1 electron? Or 2 electrons. Right, you gotta, so I have -1 on this side. I can't make something plus with adding electrons. So I have to add 2 electrons to the left side so that way I've got an overall -1 charge on the left side matching that on the right. All right. Any questions so far? So we've done Mohi. Here's another thing you can look at when it comes to balancing redox reactions. because redox reactions are always giving off, are always resulting in electrons being removed. Okay, you should always have your electrons on the right-hand side of the arrow for oxidation half reactions. In other words, something's getting oxidized in the process, you've got these free electrons now stripped off. And for the reduction half, the electrons are always on the left side. Okay, so you can always think redox left right. Okay, redox. Okay, left hand side of the arrow for the reduction, where the electrons go. Electrons always go on the right hand side for oxidation. Okay, right, and you can do redox. We will, left, right. Right, just like that song from Queen, We Will Rock You. Right, so instead of rock you say redox, left, right. And so if you're singing out the song, you know, we will, left, right. Read dox, left, right. Okay, so,
for the redox, for the, can you explain how you got 2E?
right, so overall charge on this side, -1. Overall charge on this side is now what? 2 negatives, 2 positives, plus another negative.
Oh, okay. That's
Right, that gets me also -1 on that side. So I'm just looking at all the charges now. When it comes to the electrons part, balancing the electrons, or balancing the charges using electrons, I'm just looking at all the superscripts for the charges. Now, keep asking me those questions though, because this is just an exercise in accounting, ultimately. So now that we have our half reactions, there's one last thing we got to worry about, and that is do we have a conservation of electrons? And then imagine this being a circuit, and electrons are leaving one part of the circuit and going to another side of the circuit. Well, we have to have a conservation of the electrons, so that when we add these two half reactions together, the electrons should cancel. So what can we do to multiply one or both of these reactions by some number to make the electrons the same for both the reactions? So this is 6. Well, 2 multiplies into 6 by 3, right? So what I'm going to do is I'm going to go ahead and multiply the bottom reduction reaction there by 3. So that now, when I add these two half reactions back together again, I can cancel out the electrons. So with redox chemistry, when you look at a redox reaction, you never see the electrons, right? It's just understood that they're there. And there's a reason for that. It's because when you re-add together the half reactions, the electrons should cancel. Okay, so adding these up now to get us to, we have oxidation, reduction, now getting us back to the complete redox. All right, adding these together now. Okay, so looking at our waters, we have actually, let's see, we have 6 electrons, right? So we'll do that first. Okay, so these 3 just coming from this half of the arrow, right to left side of the arrow for the reduction. And we have to add these to, I'm going to run out of space here. Adding these to the 5 waters. Alright, so that's our left side of the arrow, adding everything from the left up and putting it down here. Huh? Oh, you're right. Yes, we do. So what should this number be now for the H+? That should be a 6. And what should the number in front of the hypochlorite be? 3. Thank you. In my desire to fit this all in, I left out that part. Okay. Okay, so 3 hypochlorites. Okay, then 5 waters. Plus the chromium-3 oxide. Okay, and we're just going to go ahead and have to write the rest down here. Chloride, I have 3 chlorides now. I've got 3 waters. And I have 2 chromates. Plus 10 hydrogen ions and 6 electrons on both sides. So what we're going to do is we're going to simplify this down a bit. Okay, if I want to cross things out, can I do that? So electrons, we can get rid of those. Those both cancel on both sides of the arrow. For the H+, this 6H+ here reduces this 10H+ to 4 on that side. For our water, these 3 waters here will cancel out and make this a 2 waters there. I think that's all we can do in terms of simplifying this. Okay, so in acidic conditions, we have 3 hypochlorites plus 2 waters plus the chromium-3 oxide, and we're going to end up getting 3 chlorides, 2 chromates, and 4H+. So it really helps to try and simplify it down before you start worrying about basic conditions. So I'm going to go ahead and rewrite that up here. Okay. Okay, acidic. Let's just do a double check, make sure we're balanced. 3 chlorines, 3 chlorine atoms. Let's see, 3 plus 2 is 5, plus 3 is 8 oxygen atoms. 2 times 4 is 8 oxygen atoms. Okay, 4 hydrogens there, 4 hydrogens here. Right, so as far as the atoms go, I think we look balanced. 2 chromiums, 2 chromiums. Charge-wise, we got 3 negative charge on the left side, and we have 4 negative, but the 4 plus here neutralizes that, so we still have a 3 negative here balancing out the charge too. So that's in acidic conditions. What about basic? Well, before I go into basic, any questions up to this point? Hopefully I'm going slow enough and stepwise enough to where you're able to follow me. It's a lot of steps, but if you once you get used to it, it's a pretty easy process. You just got to remember Mohi. And you know what happens when you go to basic conditions? It becomes Mojito. You add the O, and Mojito kind of sounds like mojito, which we're around the time that some people would have, probably may have one, I don't know. It's not 9, 10 in the morning, you know, with the orange juice, you know, anyway. For those of you who are legally old enough to consume mojitos. Okay. just thinking, I don't know, probably expressing too many thoughts there. Okay. So how do we go from moji to mojito? All right. So we add OH to both sides, enough to neutralize all the H plus that's in this reaction. So H plus, we got 4 of those. So how many hydroxides do we add to both sides? 4, right? But we have to remember, we have to add the OH minus to both sides, right? That's what a lot of people forget. So we're going to go ahead and add that. So I'm going to add 4 OH minuses to the left, along with my 3 hypochlorites. And my 2 waters. And my chromium 3 oxide. Plus my... Alright, so add 4 OH minuses. This ends up becoming 4 waters. Alright, everybody okay with that? So now that I've got 4 waters here, I can cancel out more water on the left side. So these 2 cancel out, and this 4 becomes a 2 here. So my final basic is going to be 4 OH negative, 3 hypochlorite, chromium 3 oxide, 3 Cl negative, and the 2 water. Alright, so this problem asks for balancing out the basic conditions, but I figure if it asked you for acidic conditions, you would just stop here. Alright, at the acidic point. Question, yes?
So when you multiply by 3, why did the water have to multiply by like 15?
When I multiplied by 3 here,
So why does it become like 15 waters?
well, 3, so you're multiplying all the coefficients by that number.
Oh my bad, I'm looking at the oxidation.
I see.
I see it. Never mind.
Yeah. Oh, I see what you're saying. You're saying, why not multiply 3 by 5 over here? And that should give you 15 waters. Yeah, but we're not multiplying that. Yeah. Yeah. Keep asking those questions, though, because obviously there's a lot of writing here, so.
I'm just thinking of the adding the electrons to balance it out.
Right, so adding the electrons, you're looking at the overall charge. So just to revisit the electron addition, so we added 6 electrons to the right side of the oxidation half reaction because the left side of the arrow for the oxidation half was neutral on this side. You can see that, right? There's no charge appearing on anything here. You can see that, right? It's neutral. On the right side, I've got 2 times the negative 2, which is minus 4 from that. And I've got 10 plus 1s here. You can see that, right?
So you would just
So adding the 10 plus and the 4 minus together collectively gives me still a plus 6.
okay.
And to get rid of that +6, I'm gonna add 6 negative electrons